Let's do this problem fairly quickly, as best we can. And this will probably be the last one that we do off of these sections. I'm going to make sure the volume is running okay. Alright, seems like it is. So let's go ahead. Do a copy of the picture. All the information that's necessary is sitting there. The computer I have, for some reason, is fairly slow and bogged down right now, but that's not too much in the way of abnormality. So the first thing I'm going to do is I'm going to approach this with the mindset of an instant center. The same thing I've done before. I'll go ahead and make it full screen. So I know this velocity is going to head off this way. So again, now I ignore everything. I know this velocity will probably either head this way or it'll head that way. In either way, if I draw perpendicular to it and forget these, in essence, let's do this so that you don't get distracted from the drawing. What we're going to do is something interesting here. Well, first let's try it this way. Okay. Try it again. Again, this computer is very draggy. I'm going to pop over here. So if you have this, you now can remove your thought. Hang on, I am going to pick up something real quick to make this go a little better. Okay, I'm back. So, what you do, if you have 2 points, you do an instant center. Well, this is not working. Okay. And I'm going to have to find some solution towards this, but maybe next time. And there's what I'm looking at. Okay, now if I come in and go back to the geometry, I realize that I've got 60 degrees here. That gives me 30 there. That tells me that this is 1 meter. Okay, this is not necessarily 90 degrees. If I look back at the original drawing, this and this is not necessarily 90 degrees. So you can figure out the trig in order to find this distance and this distance. Now, I went ahead and I decided to make things simple for myself and draw it to scale on a drawing. And these are the 2 distances I got. Now, I did this because one of the things that engineers need to be able to do is this. This is something that seems to be missing in the engineering curriculums across the country. What I term is they use the BOB method, not because that's my name, because they use the back of the book. We're constantly looking, or you could say we're looking for SM methods, solutions manual. You can go find the solutions manual and find the problems work, or there are many other sites that I won't tell you about, but you're probably pretty well aware of them. You generally look for a number, and you're working yourself towards that number. Along the way, you're checking, your way of checking is to find the final answer that you got it. When you're working in the real world, there isn't a method of coming up with an answer that doesn't exist. So what you need to be able to do is this method, check along the way. So as you check along the way, you got to find certain ways that you can come up with the solution in two ways to check yourself. Okay, you can use law of cosines and sines here. You can go through here and say, okay, if this line is 180 degrees across to here, and I know if I do this, then this is 60, and this is 45. That makes this 180 minus, I'm just going to do this. Again, this computer is slow. I don't know why it has a faster processor than the other one that I use, but it is painfully slow and very annoying. So that's the angle there. Now, that leaves you with this angle. Okay, so we might as well do this real quick. Okay, this other method I'm trying to do is not working, so let me take this off. I need to find some type of method of fixing that. So if I do all this, I don't know what happened here. I hit the, so that's 75 degrees. This is 60 degrees. That's 45 degrees. That makes this one 180 minus the 60 minus the 75. Or 45 degrees. Now that was a stupid thing to do because actually this is opposed to that. So now if we back this away and we look at this, we recognize that I have this line is that one. Oh geez, this is going to be very painful lecture. And this line is that one. So the angle between them is going to be the sum of 45 and 60, or 105. That leaves 105 plus 30 gives you 135. Take away 180 gives you back that this one is 45. Now, that means I know all the angles in one side. So I'm going to go ahead and list this one as D1, D2. Now, D1 over sine of 30 is equal to 1, which is this one, over the sine 45. So let me see if I can hammer this out. Now, at this particular point, it may be better to go to octave. So who knows how long that's going to take to come up. Looks like a while. Good grief. Well, next lecture I'm going back to the other machine. It seems to be able to handle this a little bit better. So let's slide back to here. Now this is forced into a full screen mode, so I'm going to have to drop it out in order for Octave to sit on top of it. And so sine a degree of 30 divided by sine of degree of 45, and there's a 1 in there. So guess what? 0.707. Now, want to go look at it. That's exactly what we have right there at this point right here. So we checked it. We did a cow method. Check along the way. Now, D2. Now, the drawing over there says it's 1.3 something. So D2 is directly across from 105. So take the same thing, 105, 1.366. Now, I found this instant center, and I found its distances. Look at that. Oh gosh. So as I draw that, there's a delay. Boy, this is going to be annoying. It's going to test my patience. So it turns out, okay, now that I've found my instant center, he gave me enough information for me to determine what that velocity is. So the velocity at B is equal to omega r, where omega was 4 and r was 0.5. So I think I get about 2. So that's the velocity right here. So what is omega C B? This link. Remember, that is this link. So it appears like you could do it BC, CB, it doesn't really matter. But it appears like this triangle is rotating about this instant center right here. And I've drawn it I've drawn it the other way, so it actually rotates this way. And again, if I want to keep my sign convention the proper way, this is a positive rotation. So I've essentially got a negative rotation, but in this connotation, it doesn't matter. So we look at this thing, we see that it's sitting at this point. Velocity, again, is equal to omega r. There's my r. So I get a 2, because that's this velocity. Okay. Don't know what happened there. Okay, so let's try that again. We get a 2. This is the omega. 2. The omega and 0.707, which gives me this omega, BC, equaling to 2 divided by, let's go back, take our 2, divide it by 0.7, I got 2.8284. 2.8284. Now, I'm going to highlight what I need for the next stage. I don't know what this little rotating thing is. Sinking. That may be why. I don't know what's going on, why it's so slow. So, if we look at this, we can say to ourselves, well, let's go ahead and do velocities here. I'm going to, again, do this. Well, okay, so everything I've done is fine. Now, I'm going to move over here. I'm going to come back and now approach the problem the other way. Velocity of B is equal to velocity of B, relative to A, plus velocity of A. I will definitely be switching to the other computer next time. Now, this is omega AB, which is given, crossed with R, B to A, plus velocity A, which is the velocity at this point, is non-existent. So now, I need to go back to this concept right here, and I'll just copy it if the computer will allow me. And in this particular case, this means that omega AB is positive. Why? Because it's rotating in that direction. So I get a 4. Now, I've got to draw a vector. Starts at A, goes out here to B. So, that means a vector that has an x component this amount and a y component that amount. Well, this is, since the length of this is 0.5, each one of these and 45 degrees between that and the vertical or horizontal, that means you get 0.5 over square root of 2. Okay, so, or 1 over 2 square root of 2, which I don't know which one to do. So I'm just going to put in as 0.5 over square root of 2, 0.5 over square root of 2, and I'm going to leave it like that. The next thing I'm going to do, I'm going to come back and start making use of a interesting thing here in Octave, MATLAB, whatever you want to call it. I'm going to come up and call this omega AB. Pretty boring. It's going to be 0. Here, I'll do it with this. 0. Well, if I do it with the commas, I can see things on the line a little more. And it's a 4. So there's my omega AB. R BA is equal to 0.5 divided by square root of 2 and a comma 0.5 divided by square root of 2, and then I don't have a component going into the z direction. So if I want to do the cross product of this, I got to make sure omega AB comes first because it's to the left of RBA. If I didn't, I would interchange those couple of rows, RBA, and put a close bracket, end up with that. So in effect, let me find my pen. Okay. I get minus 1.4 I plus 1.414J. And that's all I get. So if I really want to hold on to that, I will highlight it. This is going to be important in a little while because now I need to go in here and do the second phase of this problem. The second phase is related to the fact that B and C are on the same link. Because of that, you know what I'm going to do? I am going to do this to allow myself a little bit more space. I'm going to say these should have been vectors. I'm going to do this. Now I will highlight all that because that's going to be used in a little while. That'll leave me this space to the right here in which I'm going to take off and write velocity of C is equal to velocity of C relative to B plus velocity of B, which I have below. Want to write it again, it would be velocity of C equals to omega BC crossed with RBA, plus velocity of B, which I can grab from before. Given that that's the case, I can turn now and go ahead and do things like so. Okay, if I look at this, what I'm interested in is what is a vector that originates from, I don't know why I copied that. This should have been C B, originates from B, points to C. So here's your vector. Well, you got a component that's this much, and you got a component that's this much. So what do you get? You get, here, I'll come up here, RCB equals to, the length of this is 1, so that's kind of convenient. So what you see here for the x component, which usually it's kind of, the x is listed usually first, you get cosine of 60. And it's going to the right here, but the other one is the sine of 60, and it's going down. And what you see here is I, J, and K. Now, I don't know its direction, but if I assume it always to be positive, which in this, it's best to do that because now you're dealing with a mathematical situation. And here you get cosine 60 and minus sine 60 and then 0. Now, since this is unknown, how do you deal with this in something like MATLAB? Well, one of the things you can do is do this and put a 1 in here. Now, if you multiply this times this, the fact that there's nothing here and nothing here, but a 1 here, you'll find out that this is okay. So go into MATLAB there, and you know what? We can just do it like this, since we, well, all right, let's do it this way. RCB is equal to the vector cosine degree of 60, then minus sine degree of the same 60, and then nothing. So you get that vector. Now what I'm going to do is I'm going to cross the first vector, which is a 0, 0, and usually I'd put an omega BC here, but I don't have that, so I'm going to put a 1, and I'm going to cross that vector with RCB. Okay, 0.866, hang on, let me find my pen, 0.866 omega BC I plus 0.5 omega BC J. One of the things about velocity of C, okay, if you look at this, this thing has to go this way or it has to go that way. Here, I'm going to be rigorous about my coordinate system, and I'm going to assume it to go to the right because it lines up with that. So what I'm going to do is velocity of CI goes to the right. Now, I'm going to go ahead and take this thing and put over here. But before I do, I'm going to do a cow method, check along the way. Okay. A vector, A, crossed with the vector, B, two vectors, you cross them, A and B. You take your fingers, you curl from A to B, your thumb points straight at you, that vector. C is perpendicular. If I turn my head in this perspective, this is what I would see. I would see a vector C. I'd see a vector B here. And I would see a vector A here. Now, this is a three-dimensional drawing. You sweep your hands here. This vector C is perpendicular to both A and B. I can't draw a good thing of your hands, but here's your thumb. Here's your wrist. You're curling your fingers like so. I'm not good at drawing. So here's your hand. You're curling your vectors from A towards that B, and your thumb points along C. These two vectors are perpendicular, meaning the result of a cross product, which is this, a result of that cross product, is such that it has to be perpendicular to the first vector, and it has to be perpendicular to the second. So let's take this, multiply times this, multiply this times that, and add them together. Now, I have numeric values here, and I have, but what I need to do is the first thing I see is the sign. I get a minus sign here, plus, so there is, this component is positive, and this component is negative. That's the first thing I see. So I'm pleased about that. The second thing is the actual values. If you went in and went to Octave, MATLAB, whatever you want to call it, and said cosine degree of 60 times 0.866 is that the same thing as 0.5 times the sine in degrees of 60. Well, it turns out it is. I mean, if I carried that 0.866 plus more digits, they would end up carrying, it would end up carrying more. So in fact, this check along the way is the minute you get that cross product, you dot it with the, I usually dot it with this vector because this one basically is too easy. It has 0 here times whatever, 0 here times whatever, and then the k component. Well, that doesn't get you much as far as checking. Excuse me. So that's a way you check along the way. Okay. Finally, I can add this component back over to here. So I can add the point. I'm going to go ahead and drop that and add 1.414i plus 1.414j. That's because this is velocity of b, and this was the velocity of b from last time. Now, I didn't check along the way here from this velocity, but let's do that real quick. If in fact this is your situation, the velocity should go this direction, which means it should have a component going in the minus x direction and the positive y direction. Since this is 45, this will be 45. They should end up being the same value, but at least visually I can check to make sure that that makes sense. Now I'm stuck with just solving an equation. So I'm highlighting the I components, and then I'm going to highlight the J components. And wow, okay, so from the J component, I get 0.5 omega BC plus 1.414 gives me nothing. because there's nothing over here on the left. Which tells me omega BC is equal to, wait, this is BC, right? Yeah, this is BC. 1.4, okay, 1.414 divided by 2. Is that right? 2 divided by 2? No, divided by 0.5, sorry. Yeah, multiply times 2. Well, divide by 2.828. 2.828. Hang on. Let's momentarily check back. And if you notice from the instant centers, the check as we go method, you got the same thing. So now, there's one thing that we didn't do in this instant center that we could have done, and I just didn't do it. But I can go back and do it, and that is I didn't actually find my velocity of the C. But if I wanted to do that, velocity of C is equal to 2.8284 times this distance, or arm, of 1.366, which should give me, now I'm back at the instant centers, 2.8284 times 1.366, 3.86, and I'm too tired to write the digits. And so now we come back and we construct the I equation here, and this time I get velocity of C equaling to 0.866. Hey, look, omega BC, so I can put 2.828, but there's also knocking off 1.414, and so I get velocity of C out of this of 0.866 times 2.828 minus 1.414. I get 1.3. So I've got a problem here. 1.3, I lost track of it, 3.5. Okay, so suddenly I got a problem. I get two different velocities for the velocity of C. Let's see if we can figure out why this, what is going on here. Let's take a real close look here and see if I can find the error. I got the first equation out of there. One of the things I did right off, did I do this the wrong way? Okay, let's see. Carrying this in, did I type it into there? I did type it in there correctly. Let's see. So here's the situation with check along the way. Which one would I believe? Right now, I am inclined to believe this one over this one right now. So I won't feel comfortable about the answer until they both equal each other. Now, I can check the back of the book, and I might do that in a minute, but right now, I'm still going to spend a few minutes here. Okay, velocity C, I put the velocity B over there. I did the check here. I got my Omega BC. Put my Omega BC back in here. And one of the things I think wait a minute. Let me make sure I typed in that correctly. There is something that's a little disturbing to me at this point. And let me look back at my instance center. Yeah, I am going to tend to believe the instance center at this point over the other term. Let me look at my drawing. 1.366. That's, I got that. I checked that out. I'm looking at Omega BC 2.82. I got the same thing here. The arm. So there's got to be something going on over here. Let's keep staring at it. I have not had caffeine this morning, but grab the green. Now, did I? Okay. Well, right now, I can't figure out what it is. I may pick this up because I've got to go off. I may go back and look at this in the interim. 0.866 minus 1.414. I may go ahead and pick this back up on Monday. So we may do a streaming lecture from here on Monday. And I can pick this back up on Monday. So as you can see, I'm going to go ahead and drop the lecture here in a second and leave you with hanging. But what you'll see is the concept of check along the way is a very reasonable concept. If I had done this problem, I had no back of the book answers, I could just write that out, and so somewhere I have messed up. But at this point, I know to stop and take a look and figure out where did I make a mistake, because I truly believe or don't believe that this is the correct answer. I do believe that this is the correct answer. As it turns out, moving into the accelerations, which we'll do next, the velocity of c isn't necessarily needed. The omegas are the important part. So if you were looking at the important parts, it would be this, moving into the acceleration, this, which we verified, and that was given right up here. So I'm going to go ahead and drop it. I'm going to come back. The first thing I'm going to do on Monday is resolve this. And since I'm still working this problem, I'm going to still use this laptop. So things are going to be a little frustrating for me on my end. I'll change back to the other one on, I guess, next Friday, because we'll have a in-class session on Wednesday, but not Monday. So I'll leave you hanging, and we'll figure this one out later.